Hello there, my name is Thomas. I'm from Investment Excel, and today we're going to look at regression and statistical analysis. Particularly, we'll look at OLS estimation and ANOVA. This topic is a standard topic, although there can be some statistical intuition slightly challenging, and I suggest other sessions if you'd like to get a brief recap of some statistical basics. We have several topics on investmentexcel.com in the educational category and also otherwhere in the popular topics category. Alright, this video and the Excel workbook are available, of course, on investmentexcel.com, but also on spotify.com. Let's look at a simple linear regression with a stock price being modeled on the GDP level. We look at history, 25 years. We have a stock price, and we have a GDP. So now what I want to do is to build a linear relationship between the stock price as a function of GDP. That is, the stock price is the endogenous variable and GDP is the explanatory variable. Before going into any statistical considerations, let's just look at the OLS, which is essentially just a fitting technique where we try to get the model as close as possible to the stock price by minimizing for every observation the distance, graphically speaking, between the observed level and the model calibrated level. So we do that for all vertical distances, and we sum it. And then you might think, okay, they will net out in the sum. Yes, that's correct, and that's why we square it. So every distance from the actual level, in this case the actual stock price, and the model calibrated or predicted stock price, is squared. And when we sum them and minimize that sum, we will get a fit as good as it gets. In this case here, in the graphical representation, Excel has already calculated a best fit for prediction of the stock price, stating this. So a constant at 282 and a slope estimate of 3.22. The way Excel does this, or the way you can have Excel do this, is by first making a XY scatter plot. This is just one type of graph. So GDP on the x-axis, stock price on the y-axis. So you see this nice plot, and you might see some kind of, at least there's a positive relationship. As GDP grows, the stock price goes. But we have assumed that there is a linear relationship. So let's see if we assume that, what Excel calibrates the parameters to. Choose linear, because this is a model we like to build. We could have built exponential, but then it would be non-linear regression. Now it's linear, and I want Excel to display the equation, and why not also a measure of how good the model is on a scale from 0 to 100, or from 0 to 1. And could you please, yes, very good. And here it is. Of course, we still have the same result as before. Now I also have the R squared, which is a measure of the goodness, as we say, goodness of fit, and we say this has to be above 70 to 80, 0.770 to 80. So clearly, already now we can see this is not a fantastic model. But that's not so important. The important thing is to learn the technique. And the technique behind Excel's results here is, as I said, build a model. And I just have some start values here, arbitrary start values. And I just have the linear formula up here. So you see that it's the GDP, the only exogenous variable being in the model. And for now, I just calculate the model prediction of the stock price on all 25 observations. Then I take the residuals between the stock price and the model price. But this is not the one that I want to minimize the sum of, because I will have the netting problem. We have to square them first so that there will be no effect from netting. And then we have a sum of residual squares down here. And now if I minimize this, I minimize the distance between the stock price and the model price. So on the other hand, the lower this is, the better the model is in predicting on average. And this can be done in several ways. I will just show how to do it with the inbuilt function or inbuilt algorithm in the solver. And you can find the solver, if you don't have it in your data category, you can find it under File, Options, Add-in. But back to the minimization problem. Set objective, the residual sum of squares, and minimize by changing the only two parameters in the specification of the linear model, beta 0 as a constant and beta 1 as a slope parameter, estimate, and no constraints. And let's see, if we are lucky, we will end up with the same estimates as the estimates in the graph from Excel. And you see, we get more or less the same result, but not perfectly the same result. And I have no idea why. I will just make one check just to see if I got this right on the, this was right, this was right, then the problem is, I guess, somewhere else. But it could be a rounding thing. At least they are very, very close, and the beta 1 estimate is correct. Now here we have the stock price represented by the gray line, the gray graph, and we have the model. So this is how good or bad, whatever you like, the model is in describing the stock price within the sample. Another thing is always what happens tomorrow. But first we have to make sure that we have a good model built on the sample. And that goes also, that can also be measured on statistical properties. First, and I will not show it, but just note that the two estimates here, they are both unbiased predictions of the true beta 0 and beta 1 in the population. That is the model or the relationship that we are trying to explain, the linear relationship, but with some uncertainty, because we can never be sure what the real price is. This is nothing more than a sample from a statistical distribution that we assume is represented by this model. The standard error of the model, that is the uncertainty around the predicted level, is 42.77. That is, if we use the model to predict a given stock price, then this stock price, of course, is a statistical measure. We cannot be sure that this will eventually be the right price. It's a prediction, and the statistical uncertainty around that prediction is given with the usual normal distribution settings with this. The correlation coefficient between the stock price and the model stock price is not so interesting on a standalone basis. However, it's interesting because we can use it to calculate the R-square, which is also denoted down here as a measure of the fit. So this says, this is exactly the same as Excel has, it says at 43% of the variation in the stock price is explained by the model. Clearly, we would have liked this to be 1, that is 100%. But for 43 or 44% is explained by the model. Now, if we use Excel's built-in data analysis regression tool, we can see some other properties that are relevant for assessing the model from a statistical point of view, that is from a credibility point of view. And here we go. It's very small. I will just enlarge. So, and the first thing I note here, top down, is the R-square. Again, this was what we just talked about, 43-44% explained. Here we have the standard error of the prediction. So the model value predicted has this standard error. So prediction plus minus 2 times this would be a 95% confidence interval of the predicted stock price. Down here we have analysis on the estimates of the parameters, and we see the coefficients. I'm very interested if that is the one I have, or no, it's not. So it's in the algorithm, because these estimates, they are calculated exactly with matrix use, or at least with some closed form solutions. This is done with an algorithm, and that could be a small error. Here we see the standard errors for the two estimates, and we see some t-stats. It's a small, relatively small sample size, so we have to use t-stats because we have an unknown. This one is unknown. We use the standard error from the sample, so we use t-stat. Did we have a large sample, we could have used the z-score due to the central limit theorem. And here we see some confidence intervals. And down here lastly you see the prediction of the model and the residuals. Those are exactly the same as I have calculated here. And with these residuals you could make some graphs to see that it is centered around 0 and with a normality structure. Alright, I think that was it for now. Thank you very much.